In this session, we will learn how to solve second-order differential equations using finite difference method. In the finite difference method, we divide the range of integration into equal subintervals of length h each. The differential equation is then converted into algebraic equations, and solved at the mesh points, using finite difference formulas obtained from Taylor series expansion of a function. Now, we consider a second-order linear equation. P, Q, and F can be functions of x or constant terms. Boundary conditions are specified at 2 points A and B, which form the domain of the solution. We consider the domain from point A to B as a one-dimensional region, and divide the region into n equally spaced points at x0, x1, x2, and so on. These points are known as interior mesh points. Step size h is calculated from A and B, which is used to locate the mesh points. We replace the first and second order differential operators in the equation with central difference formula, and rearrange it to get the final equation. Central difference formula, which we are using here, is based on forward and backward Taylor series expansions, and is second order accurate. The final finite difference equation is formed on all the mesh points, and a system of algebraic equations is obtained, and solved by any of the linear solvers. Now, we consider an example of second-order non-homogeneous differential equation, subjected to boundary conditions. Here, the terms p and q are constant, but term f is a function of x. We divide the domain in 10 equal divisions and get the step size of 0.1. Then, we calculate the location of the 9 mesh points, where solution is to be calculated. First point x0 and last point x10, being boundary points, the solution is known. Now, we form the general finite difference equation, using p, q, and f terms. Then, from the general equation, we form algebraic equations for the 9 mesh points. We assemble the coefficients of the equation in matrix A, and the right-hand side values into matrix B. We can observe that, in the finite difference equation, first term coefficient forms the upper diagonal of matrix A, central term forms the main diagonal, and last term forms the lower diagonal. We can solve this system of equations using backslash operator, and get the solution vector. Now, we have learned that the matrix A can be formed using the lower, upper, and main diagonal terms of the finite difference equation. In scilab, we form separate single-column matrices for lower, upper, and main diagonal entries, using the coefficients from the equation, and then combine all the three using diag function, to form matrix A. Let's understand the code in scilab. Here, we define a function named LSODE, with input arguments which define the finite difference equation. P, Q, and Fx are the terms which define the diagonals of the matrix A. Arguments A and B define the domain interval, and Fa, Fb are the solution values at the boundary. First, we calculate the step size h, and then we calculate the location of mesh points using colon operator. Then, we calculate the main diagonal MD. Here in this code, for simplicity, we have assumed that terms p and q are constants, instead of functions of x. Likewise, we calculate lower and upper diagonals, and then combine all the three to form matrix A. Now, to calculate the right-hand side vector, we first check if the term f is function of x or a constant. Depending on the result, we calculate vector b. Then, we apply boundary conditions to vector b. Finally, we solve the system and get the solution. Now, to run this function, we prepare the required data. We specify the values for the input terms, and the boundary conditions. We define a polynomial variable to form the function f for the right-hand side vector. Then, we call the LSODE function and get the solution. After running the script, we see the output in the console, and a graph is plotted to visualize the results. This way, we can solve any non-homogeneous second-order linear differential equation, using finite difference method. That brings us to the end of this session. Thank you for your interest and attention.